Aloha. Welcome to our exploration of hypothesis testing in classical statistics. We'll delve into the differences between PDH and PDH and how these concepts impact our understanding of statistical analysis. Finding the p-value through hypothesis testing doesn't directly answer our research question. Our actual question is, given the data, what is the best theory to explain phenomenon? This is the probability of the hypothesis given the data, or PhD. However, the logic of hypothesis testing is structured in the opposite direction. Given the hypothesis, what is the probability of observing this data? This is PDH. These two probabilities are fundamentally different, even though they are sometimes mistakenly conflated. Consider the statement, there are gremlins in the attic, and they make noise. If this hypothesis were true, we would expect to hear noise, which means PDH, the probability of noise given the hypothesis of gremlins, is high. However, if we start by hearing noise in the attic and then conclude that it must be gremlins, we are engaging in PhD reasoning. In this case, PhD is quite low because many other explanations, like pipes rattling or a squirrel, could also explain the noise. This misinterpretation often appears in hypothesis testing. For example, we might reason if the treatment works, test scores will improve. If the treatment doesn't work, there will be no improvement. Now, if we observe no improvement in scores, we might conclude the treatment doesn't work. However, this conclusion is incorrect. Just because we observe no improvement does not mean the treatment had no effect. Other factors like external stressors or testing conditions could have influenced scores. This error is similar to a misuse of the transposition rule in classical logic, which states that if A implies B, then not B implies not A. For example, if it's raining, the streets will be wet, allows us to infer if the streets are not wet, then it is not raining. However, we cannot reverse this to say if the streets are wet, it must be raining, since other factors like a broken pipe or flooding could also make the streets wet. In hypothesis testing, a small p-value doesn't prove a hypothesis. It is the probability of observing the test statistics if we repeat the same study over and over in the long run. When the p-value is low, it means in the long run the observed result hardly happens by chance. So, at most, it merely shows the data do not strongly contradict it. At best, hypothesis testing can demonstrate empirical adequacy, meaning it can show that the data is consistent with the model or hypothesis. But it cannot definitively prove the hypothesis itself. For instance, imagine we are testing the hypothesis that a new medication lowers blood pressure compared to a placebo. If we find a statistically significant result, we might conclude that the data supports the hypothesis that the medication works as intended. Understanding the distinction between PhD and PDH is crucial in avoiding misinterpretations in hypothesis testing. This awareness helps in making more accurate conclusions from statistical data. However, because of possible unknown factors, sampling variability, or other untested conditions, we can't make an absolute claim about the universal truth of the hypothesis or saying that we prove the theory. By recognizing the limitations of hypothesis testing, researchers can better appreciate the role of empirical adequacy and avoid over-reliance on p-values as definitive proof. It's essential to consider alternative explanations before jumping to conclusions based on observed phenomena. In practice, hypothesis testing should be part of a broader analytical framework. In modern data science, it is advisable to employ abductive reasoning and inference to the best explanation, IBE, to explore alternate options. We should keep David Brewster's warning in mind. The power of a theory to explain and predict facts is by no means a test of its truth. Thank you for joining me in this exploration of hypothesis testing. We hope this discussion has clarified the nuances of statistical analysis and the importance of careful interpretation. Mahalo.